Section 4.5, optimization. Optimization refers to types of problems where you either want to maximize a quantity or minimize a quantity. And there are a wide range of applications for optimization. Anytime that you are talking about maximizing, maybe you're maximizing your profit, or minimizing costs, or anything that uses those terms, you are talking about optimization. When we are doing an optimization problem, we are going to have to write two types of equations within those problems. One of those equations is called the objective function. It represents the quantity we wish to maximize or minimize. And the other equation will be a constraint, some sort of restriction placed on the variables that will influence the outcome of the problem. We are going to go through the guidelines first, and then we're going to do several example problems. So the guidelines first start with, we need to read the problem carefully, as with any problem. Identify the variables and organize the given information with a picture. Sometimes there will be a picture, sometimes there won't be a picture, but if there is a something that you can draw a picture of, I do suggest that you draw a picture. Number 2, we're going to identify the objective function. What are we trying to maximize or minimize? And we're going to write it in terms of the variables given in the problem. Number 3, we're going to identify the constraints, and we're going to write those constraints in terms of the variables of the problem. Number 4, we're going to use the constraint to write the objective function in terms of only one variable, and that's so that we can use calculus to solve the problem. So use the constraint to eliminate all but one independent variable of the objective function. Step 5, with the objective function expressed in terms of a single variable, find the interval of the interest for that variable, or look at the domain of the function. And then step 6 is actually using our calculus to find the absolute maximum or minimum on the interval of interest. And sometimes we may need to check the endpoints. Most of the problems we do, we don't have to check the endpoints. Optimization is a really interesting topic in calculus because it is very applicable to a wide range of situations, but it can also be frustrating because every single problem looks different. You are using a different equation for every single problem. Although the process is the same, sometimes trying to figure out what the picture looks like, what the equations are, that can be frustrating. So I encourage you to give yourself enough time to do this and to also be patient with yourself as you work through these problems. So instead of doing examples that are slightly different from your homework problems, I'm going to go directly to your homework and do examples from my solutions that I have posted. If you want to go into MML and start trying problems and refer to my solutions and then listen to this video of me describing my solutions, then you're welcome to do that and go back and forth. So I'm going to skip down to number 3 in your homework. You may have a different number here for 64, but the gist of the problem should be the same. And the guidelines for optimization are good, and you can step through the guidelines. Sometimes we'll do them in a little bit different order, but we will be doing everything in the guidelines in each problem. And so first thing in the guidelines says to read the problem and identify what you know, what you are trying to find, and draw a picture if you can. So it says what two non-negative, I think that's going to be important, so I circled that. Two non-negative real numbers with a sum of 64 have the largest possible product. So first thing I need to do is figure out where my variables are in this. And so it says what two non-negative real numbers. So I need variables for two real numbers. And so sometimes, if I were just doing this problem without MML, I would be able to define my variables as whatever I wanted. Maybe A and B, C and D, X and Y. They tell us to say that X is one of the variables. And so make sure that you read down so that you're using the variables that they use, because that'll help you as you solve the problem. I chose then to use X and Y. You could have used X and B or something else like that, but I chose X and Y. So those are my variables, and I know that they have a sum of 64. So then I can say X plus Y is equal to 64. Whenever I have a number that's given to me, that is a constraint in the problem. So they told us that X plus Y had to be equal to 64. That's a constraint. We want the largest possible product, so the product is what we are trying to maximize, And that's the thing that we're going to write an equation for, and that is the objective function. So the product, a product is multiplication, so I want p equal to xy, and if you look down here, they give you the variable p. Right, so the product of the two numbers, I want this to be maximized. That's called the objective function. And sometimes you have to introduce what you're going to call this. I called it p. Your book happened to call it p also. So now we have our objective function and we have our constraint. So the next step after you have those things is you are wanting to take your objective function and write it in terms of only one variable. And you're going to use your constraint to do that. So it says here to write the objective function in terms of x. So that means that I want to get rid of y in the objective function. So to get rid of y, I'm going to use this constraint and solve for y. If I use the constraint and solve for y, I get y equals 64 minus x. I'm going to take this 64 minus x and put it in for y in the objective function. So now I have the product equals x times 64 minus x. I substituted 64 minus x in for y. So that's what they want us to write here. The first thing that you'll see in your MML homework is they want you to write the objective function. I think they will also take, if you distribute this 64x minus x squared, they will take that also. Next thing in the process, and is a little bit weird sometimes, is finding the interval of interest. And basically what we're looking at is we're trying to find what values of x we can put in here and stay within the constraint. And so sometimes this feels like it doesn't make a whole lot of sense within the context of the problem, but you're basically looking at the domain of this function within the constraint that they've given you. So we know that these numbers have to be non-negative. They cannot be negative. It says they can be 0. It doesn't really make sense for one of them to be 0 because we wouldn't get a very large product if they were equal to 0, but we could put 0 into this equation. It is non-negative. And then it says that they have a sum of 64. So I can't go over 64, but I could go up to 64 on x, right? And I would keep this within the constraints of the problem. Again, if x was equal to 64, then y would be equal to 0, and we wouldn't have a very big product. So it wouldn't really make sense in terms of the problem, but that's the range of x values that we can use within here. Next thing we're going to do is then use our calculus to find the answer to the problem. So I apologize for this being in kind of a weird order. I was trying to fit it into your solutions. And so I also want you to kind of be able to read my solutions and kind of read my thought process here. So I'm come back over here and we take our objective function, which I expanded. And once you have your objective function, then you're going to take the derivative of the objective function. You're trying to find the maximum of this function. How do we find a maximum in calculus? We take the derivative. So the derivative of 64x minus x squared is 64 minus 2x. Using our calculus, we take this and set it equal to 0. That's going to give us the places where we have possible maximums and minimums. And if we solve this, we get x is equal to 32. So we subtract 64, divide by -2, we get x is equal to 32. Take this x, put it back into this thing that you have that says y equals 64 minus 32 is 32. So our answer is 32, but we should check to make sure this is actually giving us a relative or maximum, or the maximum on this entire interval. And so we already know our endpoints can't be maximums, because if I put in 0 for x, I'm going to get a product of 0. And if I put 64 in for x, I'm going to get a product of 0 because y would be equal to 0. So the maximum or minimum can't be at the endpoints. So then what we can do, we can either use the first derivative test. We've checked our endpoints. We know that this is has to be the actual maximum. But the other thing that we can do is we can check our second derivative. What's the derivative of 64 minus 2x? It's -2. That means that this thing is always concave down, which makes that have to be a maximum. So you'll see a little check mark on all these problems that says that I've checked to make sure I have a maximum or a minimum, whichever I'm looking for. Number 4, of all rectangles with area 289, which one has the minimum perimeter? So this is a problem where it is appropriate to draw a picture, and I've drawn a picture here with a rectangle and a length and a width. Again, I've glanced down to see what they wanted me to call some of the variables here. They want me to say P is the perimeter and W the width of the rectangle, and they say that assume that the width is less than the length if the dimensions are unequal. And so I glanced down there to help me with my variables. If they hadn't given me that direction, I could have named the variables whatever I wanted. X and Y, A and B, base times height, whatever you wanted it to be. In this case, I chose L and W. W because they told me, and L seemed to go with it. So I know that the area has to be 289, so I wrote L times W equals 289. The thing where they give you a number is the constraint. The piece where you are trying to maximize or minimize is the objective function. And so maybe I'll highlight that. Let's see if this highlighter works. And hopefully you can see that. That's the objective function. So let's highlight those objective functions. I'm going to come up here. You can't see this, but I did that also on the problem before. All right. So your objective function is the thing that you are trying to maximize or minimize. We're trying to we're trying to minimize the perimeter. So perimeter is equal to 2L plus 2W. That's the equation for perimeter, and that's your objective function. The next thing that we're going to do is we're going to write our objective function in terms of only one variable using the constraint. In this case, they want us to write this in terms of W, so we want to get rid of L. All right, so to get rid of L, we're going to divide by W, so we get L equals 289 divided by W. And we're going to take 289 over W and put it in for L in the objective function. So I get 2 times 289 over W plus 2W. At this point, they want us, and you can multiply that out, you get 578 over W plus 2W. At this point, they want us to say what the domain of this should be. So looking at this problem, we know we can't have W equal to 0 by looking at the equation. That would cause a problem. So W can't be equal to 0, so it has to be greater than 0. So that's why I didn't include 0. And then if we think about this, all right, if we let W equal 40, all right, 289 divided by 40 is some number, but that 40 would be, the other number would be smaller than W, and they want us to have the width less than the height, or the length. They want the width less than the length. And so if I take the square root of this, I get square root of 289 is 17. So 17 is the biggest number that W can be, that if we made it any bigger, it would make it bigger than the length. So 17 is as big as W can be. All right, so now we've described our interval of interest. Let's go back to the problem. I'm going to take the derivative of this. So I rewrote it as 578W to the negative 1 plus 2W. Take the derivative, I get negative 578W to the negative 2 plus 2 as my derivative. Rewrite that as negative 578 over W squared plus 2. And I moved all the way over here because I had some more room. Okay. And take negative 578W squared plus 2 and set it equal to 0. Again, we're taking the derivative and setting it equal to 0 so we can find where the maximums and minimums are. The way I solve these is I usually multiply everything by what's in the denominator to get that out of the denominator. So I multiplied everything by W squared. I get negative 578 plus 2W squared equals 0. 2W squared equals positive 578 divide by 2, take the square root, and we get w equals 17. We can then find the length by using your initial constraint. So you can always use this or even this one down below that we've already solved for the length. So we say 289 divided by 17 equals 17. Just to check to make sure that we have a minimum in this case, we take the second derivative. The second derivative of this is negative 578 w to the negative 2. Negative 2 times negative 578 is positive 1156 over w cubed, because this would be negative 2 times negative 578 w to the negative 3. And this is positive when w is equal to 17. So because it's positive, it's concave up, making this a minimum. And so we know that this w equals 17 and length equals 17 represents a minimum. And so we fill in the dimensions there. Okay, I'm going to skip to number 6. A rectangular pen is built with one side against a barn. If 1,100 meters of fencing are used for the other 3 sides of the pen, what dimensions maximize the area of the pen? So this picture is a little bit deceiving because it goes with actually the second part of this problem. And so you may be looking at this going, what are they talking about in here? So this picture goes with this. We can draw our own picture if we want up here with this one. We have the barn, and then we just have this case. So we have x, and let's call this whole distance y. So a rectangular pen is built with one side against the barn. So our barn's here. Has 1,100 meters of fencing are used for the other 3 sides. So here's the other 3 sides. What dimensions maximize the area? So let's go down to part A, skip over part B for right now. Let A be the rectangular area of the pen, X be the length of the sides perpendicular to the barn. So again, when you read the problem, come down, make sure you're using the variables that they want you to use. Let X be the length of the sides perpendicular to the barn. Write the objective function in a form that does not include the length of the side parallel to the barn. So I called that length of the side parallel to the barn as y. So we know that we have 1,100 meters of fencing. So our constraint is that 1,100 has to equal the perimeter of this, my fencing. And so this is x plus x, 2x plus y. And so 1,100 equals 2x plus y. Along here, there isn't any fencing because that's the barn. And we are trying to maximize the area. So area equals x times y. We're going to eliminate the y in this by using our constraint. So we're going to solve for y in our constraint, and we get 1,100 minus 2x. I'm going to take that, and I'm going to put it in for y in this equation, and I get a equals x times 1,100 minus 2x. I then rewrote that as a equals 1,100x minus 2x squared. I distributed the x. At this point, we should look at either of these points, we should look at what the interval of interest is of our function. Now this is where it gets weird again, all right? We can let x equal 0 in this area equation, but it really, in terms of the problem, it really wouldn't make any sense to not have x be equal to, it wouldn't make sense to have x equal to 0 because then it would just be a fence that was straight along the wall and you wouldn't get any area. So even though it doesn't really make sense within the context, it is okay within the objective function. And so this part is a little bit weird. I'm not going to put a whole bunch of stake into that. If you miss those, you can tell me and we can talk about it. The other thing is x can't be greater than 550. If x is greater than 550, it makes this piece, the y value, negative, and we can't have the side length be negative. That's just not possible. And so that's our interval of interest for this problem. So now we do our calculus. We're going to take the derivative of this. Derivative of 1,100x is 1,100. Derivative of negative 2x squared is negative 4x. We set it equal to 0, and we get x equals 275. We put it back into this equation to find the y value, and we get y equals 550. And then we check to make sure that this is a maximum. by taking our second derivative. So our second derivative is equal to -4. Derivative of 1100 is 0. Derivative of -4x is -4, so we know that's a maximum. And so we've checked our answer. We get those two pieces. Part B is a little bit more interesting. Part B says a rancher plans to make 4 identical and adjacent rectangular pens against a barn, each with an area of 100 meters squared. What are the dimensions of each pen that minimize the amount of fencing that must be used? Well, when I was starting this problem, I thought this picture went with this picture up here, so I labeled this whole thing as Y. If you're starting this problem over, you could label each of these little pieces of Y. That would make your work look a little bit different, but your final answer will not be different from mine. So let's go down to part B. So let X be the length of the sides perpendicular to the barn, and let L be the total length of fence needed. Write the objective function. So we want to minimize the amount of fence needed. All right, so let's go back up here, and we want to write an equation for the amount of fence that we have. So here's 1x, 2x's, 3x's, 4x's, 5x's, and then I called this whole thing y. So I said 5x plus y was my length. That's my objective function. So let's put that in pink again. Here's my objective function, 5x plus y. If you labeled this little piece right here as y, then you would have had 5x plus 4y is your length. My constraint is that I know that each of those little boxes has to have an area of 100. And so I say x, and in my case I said y divided by 4, x times this length, x times y divided by 4 has to be equal to 100. Or x times y is equal to 400. Either of those will work. They're basically saying the same thing. X times y divided by 4 equals 100, or x times y equals 400. In either case, we solve for y, and we get y equals 400 over x. That is our constraint. We're going to put that in for y in this equation. And now we go on with our calculus. So I just wrote this with the 400 over x, and I wrote it as 400x to the negative 1, so I could take the derivative. Derivative of L is L prime is 5 minus 400x to the negative 2, which is 5 minus 400 over x squared. I set that equal to 0. When I set that equal to 0, I end up getting x squared equals 80, or x is equal to the square root of 80. I'm not sure what the program will do, if it will let you put in square root of 80. If not, you need to take out perfect squares. So this is the same thing as the square root of 16 times the square root of 5. And then square root of 16 is 4, and we leave the square root of 5. So that's where we get the 4 root 5. Take that 4 root 5 and put it back into our y equals equation right here. So I get y equals 400 divided by 4 root 5. I get 100 over root 5 if we rationalize this. Another thing I don't know what it's going to do is if you gave it an answer like 100 divided by square root of 5, if it would allow that. I'm not sure. If I rationalize this, I get 100 by, rationalize I mean multiply by the square root of 5 over the square root of 5. When I multiply by the square root of 5 on the top, I get 100 square root of 5. Square root of 5 times the square root of 5 is 5. And 100 divided by 5 is 20. Now this is the length of the entire side of that thing. So if I want the length of just one of those little pieces, instead of all of this, I want the length of just one of those, I'm going to have to divide it by 4. So over here I took 20 root 5 and divided by 4 and got 5 root 5. Again, if I want to check to make sure that I have a maximum or minimum, in this case I want it to be a minimum because I'm minimizing the amount of fence, I take my first derivative and I take the second derivative. So the derivative of 5 is 0. Derivative of negative 400x to the negative 2 is positive 800 over x cubed. Since x is positive, 4 root 5 is positive, this whole thing is going to be positive, making it concave up, making that a minimum. So that works. All right, I want to skip to number 8. Number 8 says, what point on the line y equals 5x plus 2 is closest to the origin? So I put a tiny little graph in there, and we are trying to figure out what point on this line is closest to the origin. Now, I originally just put a point here, x, y, and drew a distance there, but it could be positive and negative values, and if you look over here, points over here are closer to the origin than points up here. So they probably are going to end up being negative, but any point on this line can be described as an x value and a y value. And I want to know something about the distance from this point xy to the origin. And so we have the distance formula. If you don't know the distance formula, you might look that up. It comes from the Pythagorean theorem. It's just a different way of writing the Pythagorean theorem. So distance equals the square root of, and you take the x minus the x value, x minus 0 squared, plus y minus 0 squared. So really that's just drawing a triangle, x, y, x squared plus y squared equals that distance squared and taking the square root. So this represents that distance that we're trying to find closest to the origin. So we're trying to minimize the distance. So this is our objective function. Right? And we can write that as d equals the square root of x squared plus y squared. And I don't know where I wrote that. Let's go ahead and write that in here. This is the same as the square root of x squared plus y squared. Well, our constraint is that y is equal to 5x plus 2. So this is a little bit different, that they didn't give us some number here, but they did tell us that y has to be equal to 5x plus 2. So I'm going to replace y with 5x plus 2. And when I replace y with 5x plus 2, I get the square root of x squared plus the quantity 5x plus 2 squared. If you square that and combine like terms, you get the square root of 26x squared plus 20x plus 4. And I was trying to figure out the domain of this. What's the interval of interest? What x values work in this expression? And so I graphed 26x squared plus 20x plus 4. And what I found out is 26x squared plus 20x plus 4 is always above the x-axis. It's a parabola that is above the x-axis. So it's always positive. So any x value will work. And so this distance can be, we can put in negative infinity to infinity is the interval of interest. Now, do we think it's going to be way far away from here on this line? No. Or way far out here? No. But we could put those values into this expression. So the other thing that's interesting about this type of problem, and this is true I think on one other problem that you have to do, is that if we have a square root and we have our objective function and we want to take the derivative of this, we can use the chain rule to take the derivative of this, and you would get, this would be da 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 to the 1/2, bring the 1/2 down in front, 26x squared plus 20x plus 4 to the negative 1/2, multiply times the derivative of the inside, and so on. Well, let's make our work a little bit shorter by recognizing that if I have the square root of a number, and we want to make it the smallest possible thing that it can be, we want the distance to be the smallest, then we want to make what's inside of here the smallest. So what we do is we basically ignore the square root and we just look at what's on the inside of this. And so I called it I for inside, and I took the derivative, and I wrote it here. I said if we minimize what's on the inside, we will minimize the entire radical. And so I took this I as the inside, and I took the derivative of that. When you take the derivative of that, you get 52x plus 20. Set that equal to 0. We get negative 20 over 52. Reduce that fraction, you get negative 5 over 13. Now, it's not a problem if you take the derivative of this thing and have that big, long chain rule. It's just that we can save us some work if we don't do that big, long chain rule. if we recognize that we can just use what's underneath the radical. So we get x equals -5/13. And if we substitute that -5/13 back in for y in our constraint, we get y equals 5 times -5/13 plus 2. And do some arithmetic there, you get y equals 1/13. I want to check if that value is actually a minimum, so I took the second derivative of this inside stuff. Second derivative is 52. That's positive, it's concave up, makes that a minimum. And so let's just look quickly at a picture of what we just did. All right, here's this line 5x plus 2. Here's this point -5/13 and 1/13. And that is the point on this line that is closest to the origin. Any other point is further away from the origin than this point right here. So that's what we found in this problem. All right, problem number 9. A boat on the ocean is 4 miles from the nearest point on a straight shoreline. That point is 14 miles from a restaurant on the shore. A woman plans to row the boat straight to a point on the shore and then walk along the shore to the restaurant. All right, so let's look at what we have where the boat is 4 miles from a point on the shore, nearest point on the shore, so that's perpendicular. From that point to the restaurant is 14 miles, and this woman is going to row to the shore at some point and walk the rest of the way. So part A once says if she walks at 3 miles per hour and rows at 2 miles per hour, at which point on the shore should she land to minimize the total travel time? Okay, so this is kind of hard to see because there's a glare there. Let's label what we know here. So let's call this x because it said let x be the distance between the nearest point on the shore. So this is the nearest point on the shore and the point that she lands. So this distance is x. Let's see if I can write that a little bit darker. This distance is x, which makes this distance 14 minus x. That's a little bit better. Okay, and then this distance along here, since we are calling this x and we know that that's 4 by the Pythagorean theorem, this would be 4 squared plus x squared. And that's the distance there, so this would be in miles. And so she walks 3 miles per hour and rows at 2 miles per hour, at which point on the shore should she land to minimize the total travel time? So we want an expression that represents time in terms of this distance x. We know things about, we have things written in distances, but we want to convert them to times. So to convert from miles to hours, and if you remember how to do your unit conversions, if I wanted to convert miles to hours, I would have to multiply by hours over miles, right? If you remember how to do that, maybe you did that in science class. And if I do that, I end up with units of hours. So this distance square root of 4 squared plus x squared, that's the distance that she is traveling in the boat. And we're going to multiply that times, it takes her 2 miles in 1 hour. So I multiplied it times 1 hour over 2 miles, and that will give us the appropriate units. Similarly, this distance 14 minus x needs to be divided by 3 so that we get the time that it takes to walk that distance. Okay, so this is the amount of time that it takes her to row, and this is the amount of time that takes her to walk. And if we add those two together, that would be the total time that she is traveling. And now we want to minimize the total amount of time. So the first thing I did was just write this in a way that I could take the derivative a little bit easier. The other thing that we should do is look at our domain or our interval of interest. X, the smallest x can be a 0. She could row straight to here and then walk the entire time. The biggest that x could be is 14. She could row the entire time. So x has to be between 0 and 14. Now we take our time function and we take the derivative of it. We want to use our calculus now. So take 1/2. 1/2 times 1/2 is 1/4. 16 plus x squared to the negative 1/2. Derivative of this, 1/3 times 14 would be a constant. 1/3 times negative x would be negative 1/3 x. The derivative of that is negative 1/3. I think I missed saying, go back to this. When I take the 1/2 in front of this, 1/4, 16 plus x squared to the negative 1/2, I have to multiply times the derivative of the inside. So that's where that 2x comes from. Then the derivative of this is just negative 1/3. We set that equal to 0. You can follow along with this algebra. I added 1/3. I cross-multiplied here, squared both sides, and I ended up with 8 over root 5. 8 over root 5 is x, and they want you to find to minimize the travel time, the boat should land how far from the restaurant. So if this is x is 8 root 5, the distance from the restaurant is 14 minus 8 root 5. So the next part of this problem, part B, if she walks at 3 miles per hour, find the minimum speed at which she must row so that the quickest way to the restaurant is to row directly with no walking. And I think there's probably a couple ways to do this problem. I'm going to show you my approach, and if you have a different approach, I'd be interested in seeing that. I took the same approach that I took with the previous problem. I want the minimum speed at which she must row, so that the quickest way to the restaurant is to row directly. So I still want the quickest way to the restaurant, so I'm still going to use the same process that I used before. And so I'm going to use the same equation. The only thing that has changed here is that I don't know this s. I don't know the speed at which she is going to row, but I know how much she walks. And so I do the entire process, same exact process from above I did here. And what I got down to here was x equals 8 over root 5. Here is the same thing with the s in it, is x squared equals 16s squared over 9 minus s squared. If I put in s equals 2 into this, I would get this square root of 64 over 5. So this value right here would work for any value of s that we wanted to put in there. It would tell us our x. But in this case, we know that we would like for x, we don't want the person to walk at all. So in this case, x would equal 14. So I substituted 14 in for x here and then solved for s. And that's what this process is over here. 14 squared, and it doesn't go to right here. 14 squared equals 16s squared over 9 minus s squared. 196 equals 16s squared over 9 minus x squared. Multiply by 9 minus s squared on both sides and continue to solve, and you get s equals 21 over the square root of 53. Like I said, I think there probably is another way to do this problem, but this is the way that I chose to do it. If you have another way, show me, and I would love to see it. The last problem that I'm going to do with you is this number 10. I have to admit to you that I didn't really like this problem. It's also described on page 283 in the text. I think it is a little bit hard to follow what they're describing here, and then adding all of their additional information. I don't know that this problem is designed that well, but I want you to be able to go through it. You can refer to the text or refer to this video. With the use of both of those, I think you should be okay. So it says a 4-foot tall fence runs parallel to the wall of a house at a distance of 5 feet. Find the length of the shortest ladder that extends from the ground to the house without touching the fence. Assume the vertical wall of the house is 25 feet high and the horizontal ground extends 20 feet from the fence. So I think this is hard to draw because I just think it's a little bit hard to follow. Maybe you can follow it fine. They tell us let L be the length of the ladder. So L, I tried to draw a picture there. X be the distance from the base of the ladder to the fence. So X is the distance from the base of the ladder to the fence. D be the distance from the fence to the house. I don't think you need D in this problem anywhere, but you could label this as D. They told us that D is equal to 5. And the distance, the fence is not going to move, so that's always going to be 5. So you can put in 5 there. You don't need that D. That's another thing that I thought was confusing about this. And H be the distance from the ground to the point the ladder touches the house. So the house, it says the house is 25 feet high, but this distance is not necessarily 25. So h is where the ladder is, the height that the ladder is touching the house. Okay, so we want to minimize the length of this ladder. So the first thing that we can do, our objective function, is this length, using the Pythagorean theorem, we can say it is h squared plus this distance here is x squared, or x plus 5, the quantity squared. Oh, the other thing they told us that this extends out 20 feet this direction, so that gives us 20 feet in this direction, and the house is 25. I didn't mention that. All right, so anyway, L is the length of the ladder, and so L squared equals h squared plus x plus 5, the quantity squared, or L is equal to the square root of h squared plus x plus 5, the quantity squared. And if you look at this picture, you can see that there are some similar triangles in this picture, and we want to get our objective function in terms of only one variable, in terms of x, so we want to get rid of h. We're going to use the fact that we have some similar triangles here, and so we can say that h over 5 plus x is equal to 4 over x by the properties of similar triangles. So, and I wrote it backwards. I said 4 over x is equal to h over 5 plus x. And then you can solve for h in this equation. So multiply by 5 plus x, and you get h equals 4 times 5 plus x over x. Substitute that in for h here, and you get h equals the quantity 4 times 5 plus x over x, the quantity squared. I would be okay if you left it like this. What they did is they multiplied it out. So this, if I square this, I get 4 squared, and x squared is 16 over x squared. This is x plus 5 or 5 plus x, the quantity squared. And this is x plus 5, the quantity squared, or I wrote it as 5 plus x, the quantity squared. It doesn't matter. All right, so I squared everything in here. And then what they did is they factored out a 5 plus x squared out of each of these terms. When you factor out a 5 plus x squared out of this term, you're left with 16 over x squared. And you factor out a 5 plus x squared out of here, you're just left with 1. And so that's how they got this answer right here. I think either of these should be fine, but if they don't accept this, then you do have to put it in this form. Like the distance formula problem, this is a square root. We want to minimize that square root, and so we can just minimize what's underneath it. So I took the derivative of the inside of this, I called it I, took the derivative, I'll let you go through the derivative and verify this, took the derivative, simplified, factored out some things, and set this equal to 0. So this is the calculus, the rest of the stuff is algebra. And I got x equals the cube root of 80. Again, I think I used the first derivative test in this case to make sure that that was a minimum. And so that's where I checked that. And so the cube root of 80 is the answer, but they want to know the length. So you have to take this cube root of 80 and put it into this function and solve for L, and you'll get 12.7. And I'll let you verify those pieces, right? But this one was a little bit, I think a lot, hard to follow what they were trying to get you to draw. Again, there's an example in the book if you want another explanation of how to get the answer to this problem. So again, these problems are interesting because they can be applied in a lot of different areas, but they are also frustrating because I can't give you an example that looks like every single problem that you're going to find. I've done a bunch of them. You can look up, Khan Academy has a bunch of them. If you Google optimization problems and types of problems, you probably can find videos of these. Please also ask me questions if you need to. This section is one that's more difficult but also more interesting. Let me know what you need and have a good week.